All right, workout problem 4. We've got a mass moving counterclockwise around this circle demonstrated on our diagram here. We're trying to draw the following vectors. So let's just zoom in on this guy. And so we've got our first one we'll look at is R here. So R is from the axis of rotation to our object. There's R. Right, and then we'll look at omega. So omega, we're going to use the right hand rule. We will point our fingers and curl our fingers on our right hand in the direction that we are moving. So if we are moving in this direction, right, clockwise around that circle, we'll make sure that our fingers are pointing clockwise in relation to where this object is, and our thumb should point up in the air, so it should be along the positive z-axis here for omega. So that would be in the k-hat direction for those of you guys who are thinking about unit vector notation. So next one we'll do is P, or our linear momentum. So P, if you guys remember, equals mv. So our momentum comes from, or direction of momentum comes from velocity. Velocity is pointing straight this way, then our momentum is going to point that straight that way as well, the direction of linear motion of our object. And then lastly, we have L, and we know L equals I omega, so the direction of L is also the same as the direction of omega. So there's L. All right, for problem 5, we've got a star going supernova, so its core is going to collapse from this rather large value of 20 million meters all the way down to 6,000 meters. We know the initial rotation rate, so we're trying to find what the rotation rate of the star is on the backside or afterwards. So this is going to be a conservation of angular momentum. So we're going to have the angular momentum before has to equal the angular momentum afterwards. So angular momentum before is I omega, has to equal I omega. That's 1, 2, 2. We know I, it gives this to us. This is going to be 2/5 m r squared. So it's going to be r1 squared times omega 1 has to equal, same thing, 2/5 m r2 squared omega 2. Those masses will cancel, those 2/5 will cancel, so what we're left with is just r1 squared omega 1 has to equal r2 squared omega 2. So we need to convert our omega 1 from revolutions. So we have 1 revolution rev every 45 days, and we know R1 is 20 million, so that's 10 to the 6th meters, and we know R2 is, oops, not 20, it is 6 times 10 to the 3rd meters. So when we plug all this in, we're going to get 20 times 10 to the 6th times, and then this is all squared, times omega 1, which is 1 revolution in 45 days. And that's going to equal 6 times 10 to the third squared times omega 2. And when we walk through and solve this, what we wind up with is 246,913 revolutions per day, or that's approximately 3 revolutions per second. So there's answer number 5. All right, for problem number 6, we have our bird feeder here. What we have is it's going to be spinning around. We're going to define that as positive. And then we have our little bird, and our bird is going to fly in here with some velocity and land right on the edge of our bird feeder. So in this case, we have another problem where we have a couple things happening. Then we have an event occur, and then afterwards we have some change or some new stasis of events, some new motion. So in this case, we have the bird feeder spinning, the bird flying in, the bird lands, and then afterwards the bird feeder and bird are going to spin in some new way. So we start off. This is a momentum type of problem. So anytime you see that pattern, we know that it's going to be a momentum problem. So we have angular momentum in this case because things are spinning. So we have the angular momentum before, and we have the angular momentum afterwards. When we think about this, then, what types of things have momentum beforehand? Well, we have the angular momentum of the feeder that's spinning, plus we have the bird that's going to carry some angular momentum in. Even though the bird's not spinning, as it flies straight in, it's going to land on the bird feeder and cause it to change its spin. So we have to account for that potential spin that could happen because of that bird. Then after the bird lands, what we have is we have the bird and feeder are going to have some angular momentum together. So they're a combined system at that point. So we need to look at each of these individually and figure out what they're going to be. Well, let's start with the feeder. So our angular momentum for the feeder, because it's an object and it's spinning, we're going to use the equation I omega. So this is going to be our initial spin times I. In our problem, we're given the rotational inertia here. So we're given I and we're given omega. So we're going to have to convert that omega, but we'll do that a little bit later. But that's sufficient enough for us to know that we have I and omega, so we're done with the angular momentum of the feeder. So now let's look at the bird. So the angular momentum of the bird. In this case, we have an object that is moving in a straight line, not spinning, towards our object that is going to spin. So how far away it is from the axis and how much momentum it brings in. We know both of these things, so we can use our R cross P equation, which is R cross MV, or R MV sine of theta. Well, we know how far away it lands. It lands on the edge of the rim, and we know that the feeder has a radius of 0.19. We know the mass of that bird. We know how fast that bird is coming in. And so the last thing we need is to figure out what that angle is. Well, here's the thing. We know that it's tangent to our feeder. And so what that means is that if our R comes out and our velocity crosses, that R cross V vector is just going to be this guy right here, and by tangent, that means it's 90 degrees. So tangent means theta equals 90 degrees. So we have all that, which means we have the angular momentum for the bird. So now, lastly, we need to find the angular momentum of the feeder plus the bird. So in this case, after the bird lands, we have an object and it's spinning. So that means that we have I omega, which is what we should use, omega 2, that's our final omega. And this I, this is the new I. This is the I of the feeder and the bird. So we need to figure out what that I is going to be. Well, we know the I of the feeder, so that's just IF, but now we need to add whatever the I of that bird is going to be. So that inertia of that bird is IB. Well, we can model that as a point mass, so that bird is just a mass sitting at the edge of our system. So I feeder plus mr squared, right, for a point mass there, and omega 2. So we have IF, we already knew that. We know the mass of the bird, we know the radius that the bird's sitting at, so and omega 2 is what we're looking for. So if we combine all of these back up into our equation, we have LF plus LB equals LF plus B. Well, when we combine these, we get I times omega 1 plus R M V sine of theta equals IF plus mr squared times omega 2. Now, the only thing that we have left is to make sure that everything is in the right units, and then we can just plug all of our numbers in and solve for omega final. So the thing that we need to convert, the biggest thing is this 5.6 revolutions per minute. We need that in radians per second. So basically we just have to multiply that by 60 seconds per minute, and then 1 rev is 2 pi radians, and when we do all that we get 0.586 radians per second. Well, now we can plug all that in and we get omega 2 is going to be equal to, now why is this negative? Well, this is an important thing. We have defined positive as going this way. So if our bird flies in opposite that, that is going to be a negative 1.1 meters per second. Omega 2 is 0.328 radians per second.